Now, I should have basically covered uniform convergence and pointwise convergence, but I deliberately avoided this. But if you go through analysis lectures, basically you will start with sequences and then you will start with what pointwise convergence is, and that leading into uniform convergence and implications and so on. But here we will just stress upon only certain ideas from analysis which are useful for us to discuss the convergence aspects of Fourier series. Okay. One of the important concepts is uniform convergence. So, let me define what this means. Given a sequence of functions f small n subscript small n x for a given tolerance epsilon greater than 0, some positive tolerance, there exists capital N such that absolute value of f n of x minus f of x is less than epsilon for every x and all small n greater than or equal to capital N, and this is basically what uniform convergence is. So, I give you some function, I give you a tolerance epsilon, I give you some number capital N, it could be a million, it could be a billion, some number. Then I take f of x Fourier series expansion, I take f n of x truncated to n partial sum, and this is within epsilon for every value of x and all small n greater than or equal to capital N, right. That means if I take the sum, it basically is bounded. This is what I mean. This is what I mean here. And if the tolerance depends upon the point, then it is pointwise convergence. So, uniform is a more sort of a more general statement, right. So, you can think about epsilon which I can give you a tolerance, and the tolerance, if it is dependent upon the point, that means if you evaluate the function and you look at the approximation, the tolerance, if it depends upon the point, that means some point x naught, I give you some tolerance epsilon which depends on x naught, for some other it is epsilon depending on x1, so on and so forth, then it is for a very specific set of points. Here it is not dependent on any point. I give you some tolerance for all points x, this is bounded within epsilon, okay. The absolute value is bounded within epsilon. So, there is another definition which I will state. A function is piecewise smooth if it is continuous and its derivative is defined everywhere except, important, except possibly at a discrete set of points. An example of this is the sawtooth waveform, okay. A function is piecewise smooth if it is continuous and its derivative is defined everywhere except possibly at a discrete set of points, at some points. So, sawtooth waveform is one of them. I mean, it is, imagine this is sawtooth waveform. Now, there is a result. So, what does it mean? The smoothness property is very important, because if it is, it depends upon the number of derivatives. If it is nth order smooth, let us take the function f of x equals x. First derivative is a constant, exists. Second derivative is 0, it is vanishing. Take f of x equals x square. Second derivative, it exists, right? Second derivative, first derivative is 2x, second derivative is 2, constant, right? Two derivatives exist, after which it just vanishes. So, if a function is nth order smooth, if all the n derivatives exist and you take the next derivative, it just vanishes, next higher order derivative, it just vanishes. So, when we talk about smooth functions, it should be really differentiable many times. Now, if you think about the Gaussian function, how many derivatives does it have? Many. So, this Gaussian kernel, it is useful in many applications in signal processing, because it is smooth. Keep on taking the derivatives, it is smooth to that extent, right. This is one of the important ideas in signal processing, and I think in the wavelets also, the Haar, for example, is not nth order smooth function. Just take the immediate derivative, it just, there is trouble at the points, and of course we can investigate the time frequency uncertainty at those points. It's an interesting exercise, but I think what you have to bear in mind is, since it is not smooth, if you want a smoother approximation, you may need conditions in creating your wavelet functions, etc. So, this is one of the important considerations in signal processing. Okay. So, a little bit of digression, but I think you have to get the idea of what smoothness is. Now, we have a theorem the Fourier series of a piecewise smooth 2 pi periodic function converges uniformly to f of x on the interval minus pi to pi. I mean, f of x equals x is not smooth everywhere, right. I mean, it is exhibiting discontinuities when you try to periodically extend it. This Gibbs phenomenon, we saw that. Now, imagine that we have periodic, is it a piecewise smooth 2 pi periodic function, and the Fourier series of that function converges uniformly to f of x on the interval minus pi to pi. We have to prove this result. So, we shall prove this theorem with the assumption that f is everywhere twice differentiable. We will see the condition why this twice differentiability needs to be satisfied. Okay. So, let us start with the function. Let f of x be summation over n a n cos n x plus b n sin n x. Now, I take a derivative 2 times this is one thing nice about these trigonometric functions. Cos becomes minus sine when you take a derivative, right? Sine when you take a derivative it becomes cos. So, taking twice derivative is not so difficult for us. So, if this is giving us a n double dash cos nx plus b n double dash sin nx, then we can relate a n double dash and b n double dash in terms of a n and b n. Okay. So, here a n double dash is minus a n times n square and b n double dash is minus b suffix n times n square. Not too difficult, just take a derivative, n pulls out, take another derivative, n pulls out, cos becomes minus sine, sine becomes cos, there is a negative sign there, it is straightforward. Now, consider summation n equals 1 to infinity absolute value of a n plus absolute value of b n. Now, this is equal to summation n equals 1 to infinity absolute value of a n double dash upon n square plus absolute value of b n double dash upon n square, right, because we have the link between a n and b n. Now, if f 2 dash is continuous, then a double dash and b double dash stay bounded by a quantity, let us say this is some m. So, therefore, B can be, did I use A somewhere earlier? Maybe I can call this A set of equation, this is I call A. B can be written or simplified as because this is bounded, this is less than or equal to summation n equals 1 to infinity say m upon n square, let us say this is m and n if you want, or you can bring in one quantity which is m, which is max of m comma n, you could do that as well, but let us just get it in this form. So, this is basically m plus n times summa n equals 1 to infinity 1 upon n square, and we know this is finite and bounded and given by pi square upon 6. It is not too difficult to prove this result. So, now if m and n are finite, this is finite. So, everything is finite, therefore, you can say that this is not heading to infinity and this is basically bounded. Okay. So, is this clear? Now, to ensure uniform convergence, we need another result, and we will prove that in a lemma. Okay. So, this is one part of it. If you look at the statement of this theorem, this says it converges uniformly to f of x, piecewise smooth. So, first we said is we want to start with the assumption it is twice differentiable, and if it is twice differentiable, we said if this function is continuous, if f2 dash is continuous, then their coefficients are bounded by some quantities m and n, and then we replace that bound through an inequality. We say that the sum of the absolute value of the coefficients is bounded. That is what we have established. That means it is finite, it is strictly less than infinity. Okay, let us get into the technical details of another lemma which is useful towards the main result. Suppose f of x is a naught plus summa k equals 1 to infinity a suffix k cos k x plus b suffix k sin k x with k equals 1 to infinity absolute value of a k plus absolute value of b k, this being strictly less than infinity. See, this condition is being satisfied in the previous result, right. We took the absolute value of the coefficients and that is finite. If this result is true, then Fourier series converges uniformly and absolutely to the function. So, basically now in the first part of the previous result we have not proved it completely, we have just established this result. We need to start with this condition here that the coefficients are bounded and then establish the uniform convergence property. So, therefore, this lemma is nested inside the theorem. Okay. I could have done a lemma first and I could have proved something, but I want you to get a feel of the flow of the theorem. So, therefore, I am nesting the lemma literally inside the theorem so that you can understand how this works. So, we will start with the proof. Let us start with our familiar inequality, which is the triangular inequality. You take absolute value of a k cos k x plus b k sin k x. This is less than or equal to absolute value of a k plus absolute value of b k, because cos and sine, the absolute value of these functions is less than or equal to 1. Okay. This is the first thing that you would do. Now, let s suffix n of x be a naught plus summa k equals 1 to capital N a suffix k cos k x plus b suffix k sin k x. Let us look at this partial sum. Now, f of x minus S n of x is summation k equals n plus 1 to infinity a k cos k x plus bk sin kx, right. If you just remove this from k equals 1 to n, you are left with the pile from n plus 1 to infinity that you need to take a sum. Now absolute value of f of x minus s suffix n of x, this is now less than or equal to summation k equals n plus 1 to infinity absolute value of ak plus absolute value of bk. But with our twice differentiability condition, summation k equals n plus 1 to infinity mod ak plus mod bk is less than infinity, right. We proved that result because that constant was heading to pi square way. Now this is easy for us. So for a given epsilon greater than 0, there exists some capital N naught which is greater than 0, so that for n greater than n naught, this implies summation n plus 1 to infinity k equals n plus 1 to infinity absolute value of ak plus absolute value of bk, this is less than epsilon irrespective of x. This is very, very important. Irrespective of x, this is strictly less than epsilon, because you could choose your m and n and all these things carefully. So this establishes uniform convergence. So I would just close the proof of this lemma here. I will also close the proof of this theorem saying use lemma to conclude the theorem. Okay. So this is a very important result. I think it is a significant theorem. It starts here, the theorem starts here and it ends after the lemma is proved and then as a consequence of the proof of the lemma. So the Fourier series of a piecewise smooth 2 pi periodic function converges uniformly to f of x on the interval minus pi to plus pi. So we will stop here.